This webinar is the result of a poll that Mark ran a few weeks after publishing his book, Crime Against Mine Planning. And the question that he posed was, what are the major factors responsible for the short shelf life of even the best mine plans? And Mark, as I recall, the most popular response was optimistic mine plan input assumptions.
Yes, definitely.
And the second, and the second most popular one was when those naughty people in production don't follow the plan. So today we would like to look at the reasons why this problem is so widespread, and also we would like to see what we can do about it. It's time for some shameless self-promotion. So my name is Hendrik Lourens. I'm a management consultant. I train as a physicist, and I have advanced qualifications in polymer science, theory of constraints, MBA, and experience in applying complexity science. So I started StratFlow in 2013, and I've collaborated with the world's foremost theory of constraints in mining practitioner, Ari van Niekerk, ever since. And StratFlow, we help miners deliver breakthrough results in safety and productivity, and we provide peace of mind to mining executives. So for 20 years and more than 80 interventions, our productivity platform has delivered plus 20% increase in output using the same resources within 3 to 5 months. And Mark, I'm going to go over to you just to do your bit.
Hi everyone, my name is Mark Bowater. I'm a mining engineer. I've worked in the Australian mining industry for about 30 years or so, all of it in open cut in both coal and iron ore, and worked in the industry for about 10 years for a couple of the big mining companies before starting my own business, my own consulting business about 20 years ago. Grew that to about 30 people or so before I sold it in 2012. Spent a couple of years outside of the industry, and in 2017 rejoined the industry, just consulting as a one-man band for myself. About a year or two ago, I decided that I guess I was a bit sick of the mining industry meeting, like, you know, what we all call the definition of insanity in terms of in the mine planning space, continuing to do the same thing and expect a different result. And in my opinion, that's what we've been doing in the mine planning space for 30 years that I've been in the industry. So I started writing some articles on LinkedIn. They seemed to be fairly well respected. And so therefore I took the step of writing the book, Crimes Against Mine Planning, which, as Hendrik said before, this webinar sort of comes out of some follow-on questions from that. Back to you, Hendrik.
Thank you. So in order to fix the optimistic mine plan assumption problem, we need to dig deeper first. And in truth, there's a gigantic elephant in the mining boardroom. The industrial age management paradigm is starting to derail under the pressure of changing societal expectations. The examples you are very well aware of things like social license to operate, employee engagement issues, and especially ESG considerations nowadays. But even the shareholders are often not getting a great deal. And if you look at this graph, this is McKinsey's Mine Lens Productivity Index, and it shows that mining productivity adjusted, even adjusted for lower grade and deeper mines, it's dropped by more than 30% from between 2005 and 2015. There's been some improvement, but most mines are still operating well below the levels, the capability that they had 2 decades ago. Now, the production supervisor's primary focus, we know, is efficient production on the mine, and decision-making and production sequencing will then tend towards decisions that favor production's KPIs. But many miners produce metal and minerals, as you know, to different specifications, each with unique quality specifications, and to ensure that we have the right product available at the right time requires a plan that will not always favor maximum productivity. And this requires negotiation during the planning stage and a realization that both the planners and production personnel will determine the feasibility and stability of the plan. And the stability of the plan and the faith production have in it can be undermined due to history. And as identified in Crimes Against Mine Planning, the production department affects the reliability by contributing to production variability, and by sometimes introducing stretch targets that are not achievable with the current way of operating. These issues then combine to reduce trust and cooperation across the silos, It's a very crucial issue, and we'll definitely come back to that shortly. Now, could it be that the mining industry beliefs on what constitutes best practice are what's holding us back from improving? We believe that this is indeed the case. And the first step then has to be to identify those erroneous beliefs and to replace them with more relevant beliefs. So what do you think about these statements? If you want to make money, most of your resources need to be idle from time to time. If a company tells me they have moving bottlenecks, they have no bottlenecks, and most resources have at least 30% spare capacity. Do you want to make money, or do you want to show off efficiencies? Now, these statements from the founder of the theory of constraints seem crazy, but in 50 minutes time, they will make perfect sense. It is actually our efforts in which we try to optimize all the parts and the departments on our mines that are holding us back. So let us assume you are a production manager and you're responsible for 6 production departments that will work in series to deliver a certain output. I come to you and I say, all right, I want you to size these 6 departments so that they run at the maximum efficiency and can deliver on average 10 units per hour. How would you size and resource these departments? Well, most people would agree that a chain that can on average deliver 10, 10, 10 would deliver the overall average of 10. So they're very happy because all the departments will produce 10 each per hour for 100% efficiency. And we surely can't do much better than that. But now there's a scientific fact around variation that industrial processes are variable. So an average of 10 means some 12s and some 0s. That gives us an average 10. And we also know that industrial processes are not normally distributed. Which brings us then to the second problematic fact, and that is of interdependence. We have to deal with the fact that industrial processes in a chain are interdependent. So if B goes down, upstream departments have to stop and downstream departments starve. And if F goes down, it blocks E from producing more, which blocks D, and so on. So if we look at 2 resources and their combined effect, we see that as green produces less than blue, blue has to stop. And every time when blue produces less than green's instantaneous capacity, green is starved and can only produce that which blue is handing over. So the combined output of these resources is the least of the instantaneous production of both, which is the red line. This is quite surprising. Now, so let's continue with these 2 resources and now add 4 more. So all these resources have non-normal production distribution. And our instantaneous output is again the lowest output of any resource at any time. And to make it really interesting, sometimes we win the lottery and by accident, we exceed our production record. You can see that in those blue sections. But it was definitely not because we planned so well or we worked so well, we just won the lottery. And the manager the next day will say, "I'll see, you always complain. You don't have enough of this, you don't have enough of that, but you can do it." And then tomorrow, well, when we look at the entire chain, we see that the output is actually 5 and not 10. Now imagine you're in charge of production, and next morning you arrive at work and you're confronted by this graph. So naturally you ask your leaders, where's my production? And what do you think they'll say? The manager in charge has many problems. Who does he hold responsible for this shortfall in production? Who does he reward for good performance? Where is the bottleneck he should focus his attention on? And what will the interdepartmental relationships and willingness to collaborate be like? What's the likelihood that decision-making will be devolved towards the lower levels of the organization? And what will the attitude be towards trying innovative new ideas? What will employee engagement and willingness to contribute new ideas be like? And how much time do you think this manager will have to focus on the future and improvement versus managing the day-to-day conflicts? And can you imagine, horror on horrors, if we were to digitize this information from all the departments, What would the manager do with this? It would be a total overload of data without any useful information. So here is a significant reason then why the optimistic input numbers are often used. The production was budgeted at 10, but the design of the system is such that it can only produce 5. So what are the manager's options? Well, given that the output is not at the budgeted level, well, they will try and enforce accountability with more KPIs on the performance of the individual departments. But the outcome is that the trust and the willingness to cooperate reduces, because we are measuring things to which people cannot perform, and the productivity and engagement drops even more. And starting about 20 years ago, the ERP systems became widely used. They had many benefits, lots of data became available, but more measurements and data do not deal with this fundamental issue that we've just seen. And the fundamental issue is that balance capacity chains are a nightmare to manage, and they are extremely unstable. And this is what the production graph looks like for a typical balance capacity chain. We have high variability in the daily output. You can see that the difference between the average and the budgeted number is greater than 25%. So we know that this is a balanced capacity change from experience, and most likely there are moving bottlenecks and definitely lots of hidden capacity. We're actually quite happy when we see a graph like that, because it means that there's lots of capacity that can very quickly be liberated. Mark, so I'm going to hand over to you to continue from here.
Thanks, Hendrik. Hopefully everyone can see my screen. So I want to take the optimistic mine planning that this webinar is about, and delve into that a bit more. And it's interesting when we think about optimistic mine planning. The first thing I think about is optimistic assumptions, sort of assumptions for production rates, etc., that we can't achieve. But there's actually a second element to that, and ironically, it was a discussion I was having with Hendrik on LinkedIn about 6 to 12 months back, where it was Hendrik who sort of said to me that losses are carried through the system, but gains are lost. And that was the first time I'd actually ever really thought about that and come across that. And so I wanted to do some more work into that. And when we sit in our deterministic world of scheduling equipment, and we have sort of buffers between activities and so on, we don't really understand the impact of these interdependencies in a deterministic world. So I've just created this this very simple example just to sort of try to highlight and explain it. And so we've got a simple example where we've got a digger that's going to dig block B, and that's dependent on 2 other tasks before we can start block B. And that is, we need the excavator that's got to finish digging block A, and the blast crew have actually got to blast block B before we can start. Now, in a deterministic world, they will all finish on time, but in a real world where we have variability, the fact is that neither of those 2 activities are going to finish on time. They will finish early or they will finish late. Now, it might only be 1 minute early or 1 minute late, or it might be a week early or a week late, but the fact is they won't finish exactly on time. That then gives you 4 scenarios that can occur in terms of the 2 prior activities finishing early or late. And the table sort of shows the late in the red cross versus the early in the green tick. And only 1 out of those 4 is actually going to lead to block B starting early. 3 out of the 4 are going to lead to block B starting late. So we actually have a probability of starting block B excavation early of only 25. And that's where we just have 2 activities in sequence, such as, for example, blasting followed by digging. But it gets worse, because what if the task is dependent on 3 prior tasks instead of 2? So not only has the digger got to finish block A, and we've got to finish blasting block B, but we've got to excavate a sump, or we've got to dewater the area, or we've got to excavate a ramp or some other thing. Now that we're dependent on 3 prior tasks, that probability of block B starting early drops to only 11% from the 25% that it was previously. And of course, that's assuming that we plan at P50, that it's a 50, our input assumptions are 50% probability of happening based on historical performance. But we all know that in the mining industry, we don't tend to plan at P50s. We always plan on stretch targets. And so it's more likely that we're planning on, for example, like P40 or something. So at P40, those two activities now have a 16% probability of starting early instead of 25%. And if we're planning at P30, it's now only 9% instead of 25. So the greater the optimistic assumptions, level of optimism in our assumptions, the lower the likelihood of achieving the plan, not only because of the optimistic assumptions, but because of the impacts of the interdependencies. So then I want to do just a simple example using a probabilistic scheduling tool to just see what the impacts were. And so I created a simple example whereby it was some activities in sequence in terms of drilling, blasting, mining waste, mining coal, sort of washing. And as I said, simple example, each of those was just a 12-day activity time period and with no buffers or inventories between them. And so what happens is that the dependencies do cause slippage in the schedule. So where we are looking to blast block F, we need the blast crew to have finished on block E, and then we also need the drill to have finished block F. And so I've run this simple example with a normal distribution on the variability and a standard deviation of about 30% of the mean. So for a 12-day task, the standard deviation was 3.6 days. And so this simulation shows the outcomes of that, whereby the mean likelihood of actually finishing the blasting of block F is now about a day and a half longer than our deterministic schedule. So the schedule is slipped by a day and a half just in those two activities. And then the slippage just continues to grow throughout the schedule. So the blasting is a day and a half late. By the time we get to completing mining the waste, it's 3.5 days. The next step in the sequence of mining the coal, 6 days. Washing, by the time we get to completing washing, we're about 8 days behind schedule. And by the time we finish the railing step in the sequence, we're about 10 days slippage after those 6 tasks that are in sequence. And we are actually only at a 2% probability of finishing on time. So that was 6 tasks in sequence of 12 days each, so 72 days. So we've had 10 days slippage in 72, or about a 14% slippage, for example. But the fact is that we don't operate without inventories or buffers. So I wanted to run a scenario where we build some buffers into the schedule and see how that works. And so I built a 5-day task buffer in between when we finish blasting activity versus when we start digging, etc. 5 days between each of the steps in the sequence. And so what it does is we still get the slippage and it still grows over time, but it's reduced. So where we had 10 days slippage before, we're now only getting 4 days instead of 10. So that's 4 days out of 72. So that's about a 6% slippage or so. And we are now about a 29% probability of finishing on time. So then if I look at that from the point of view of trying a few different scenarios of the length of buffers between the tasks, where the 0 days is the first case that we ran, where we had 10 days of slippage and we're only 2% probability of finishing on time. Second case was 5 days, where we had 4 days of slippage, 29% of probability of finishing on time. So even if we introduce buffers as large as 13 days, and bearing in mind that I've scheduled in this simple example, each task took 12 days. So our buffer between the tasks is actually longer than the time taken to carry out the task. Even at a 13-day buffer between tasks, we're still getting slippage of a day, and we're still only a 44% probability of actually achieving plan. So P50 in does not equal a P50 out from a probability point of view. Now then what I wanted to do was, so if I just summarize sort of where we're at from a mining perspective, and this is thinking about it as a mine planner in the scheme of things. So we plan generally by and large across the mining industry with optimistic inputs. in terms of production rates and our calendars and those sorts of assumptions. So we sort of already know that our plan is going to be wrong because it has optimistic assumptions built into it. And we carry out deterministic planning because we don't actually really have any probabilistic scheduling tools to use. So we're still sort of living in a deterministic planning world. But you know, as planners, we do know variability is real. We do know it's going to happen. And so therefore, we've got that combination of optimistic input assumptions and variability that's actually going to just ensure that our plan is sort of prone to even further error. And so then what do we do to cater for, and what I've described as our poor planning practices, but I want to qualify that because I'm not actually saying that that's the planner's fault. The planner can only use the tools that they have at their fingertips to use. And if optimistic input assumptions are mandated from a company perspective in terms of what assumptions should be used in the plan, that's not really the planner's fault. So when I talk about poor planning practices, I'm not necessarily talking about poor work by the mine planners, but it is a fact of life from my perspective. We do have poor planning practices in the mining industry. So we do two things. The first thing we do is we build an inventory or buffers, and we put it everywhere. So we put it in front of every step in the sequence. There'll be inventory in front of the blasting, there'll be inventory in front of the waste, inventory in front of the ore excavation, inventory at the processing plant, inventory in terms of product stockpiles before you rail, and inventory at the port stockpiles before you ship. So we have lots of inventory everywhere, and that's primarily for sort of two reasons, really. The primary reason is that we don't want anything to stop. High capital cost of all of the equipment and infrastructure, so we don't want items parking up, and also it helps our mine plan to last a little longer, what I call a shelf life. So for me, the shelf life of a mine plan is when the mine plan becomes no longer usable from the point of view of you can't base any decisions on it going forwards because it's too far out from reality in terms of the face positions for pieces of equipment and so on is so far out from your mine plan that you can't make decisions based on it. That's when you've reached the shelf life of a mine plan. So we build an inventory everywhere, but we tend to get such great variability in the mining industry, and we haven't really catered for that variability. And so we still frequently get what happens in terms of the plan actually falls over. We reach the sort of the shelf life of the plan. It's no longer useful for making decisions. So to cater for that, we build in flexibility, and flexibility is generally in the way of spare faces. So for me, it's the mine planner's equivalent of contingency planning. So it allows us to make decisions on the fly when two activities are now going to overlap and get some interaction between them. Something's going to park up or something has to happen. Flexibility allows us to change the plan on the fly without having to necessarily go and sequence the whole plan. Both of those, however, cost an inordinate amount of money in terms of building that inventory everywhere. Spare faces equals, certainly in the open cut, equals a larger void. That's money spent earlier than you need to. It is also longer haul distances, etc. So those two cost a lot of money before you even think about all the other inefficiencies that occur from what I call poor planning. And so that is, for example, equipment parking up, equipment taking shortcuts to try and just stay on plan in terms of getting the ore out that's got to be retrieved by when, and all those sorts of things. They all add additional costs in terms of from where we're at. So back to you, Hendrik.
Thank you. All done. Okay, so now that we've identified that balance capacity chains are a root cause of a short shelf life of mine plans, what can we do about it? So you remember this slide we showed before where the output is 5 and not the expected 10? Now, a necessary part of the success of our new operating system is that we have to make a distinction between bottleneck and non-bottleneck departments, and we have to manage them differently. We have to manage the overall system for flow and not for departmental efficiency. So by putting in buffers around the bottleneck department, we decouple the bottleneck from the rest of the production chain. And the bottleneck now produces substantially more than before with less variation. So you see the blue that's added. That was the hidden capacity that was not available before. So upstream departments use the status of the feeding buffer as the priority system, and downstream is the status of the space buffer. So you run or flat out or not, depending on what the condition is of that buffer. So in this way, we drastically simplify the management of the production process, and we free up time and resources. So we create superflow in a spirit of calmness. That's what we like to call it. And we now know where we should focus our digitization and automation efforts. Efforts around improving the running of the bottleneck is where we'll get our leverage results for effort very quickly. And in this example, the retro source is the bottleneck, delivering around 10 units an hour. The upstream and downstream departments need to be sized at around 12 or 13 units an hour to ensure that the buffers can be refilled quickly should a disruption occur. And this means that their efficiency will not be 100%. But given that we are now capable of bringing through 20 to 30% more production, that does not matter if you look at the actual costings involved. So do the following statements now make sense? If you want to make money, most of your resources must be idle from time to time. That would be the upstream and downstream departments from the bottleneck. And if a company tells me they experience moving bottlenecks, my view is that you have no bottlenecks and at least 30% spare capacity. Now, just a little bit more about that particular issue. So if you think of a mine, which is an open cut mine that's running in a continuous cycle between blasting, drilling, blasting, load and haul, preparation, staking, etc. What will happen is that if you have a moving bottleneck, you would think that the work would tend to pile up in front of the step that's the slowest, your capacity constrained step. And yet you find that it's not happening in the case of a moving bottleneck, it's moving. So it must mean that the average flow through the system is substantially lower than what the minimum or the slowest step is capable of. Otherwise, all the work would build up in front of that step. So we just continue. So in any serial chain, you can only optimize one particular part. And again, we all come back to the balanced capacity chain and trying to optimize everything to cost and efficiency. We should be very careful. We shouldn't waste money, but we should not go overboard in trying to optimize. So what we would like to do now is we would like to take our mind from the old world where we had a balanced capacity chain into the new reality where we have understanding of where our bottlenecks are and we are buffering and managing around that those constraints inside our system. So we have to change our paradigm of how operations are best set up and managed. We can't do this by just continuing and doing a little bit better what we did before. So what this will give us is a stable production at a higher level and greater agility inside our system and with our team of people so that we can adjust when the inevitable surprises that Mark's shown comes through. And here what you see is to enable this adjustment, this is the productivity platform or the flow room. So we need to change the cultural mindset, and it's a significant change. So to do that, we've developed the productivity platform and the flow rooms. So we always say that although theory of constraints is very important in this way of thinking, it's probably 30% of what's required. The real magic happens inside this flow room, where we change the culture and the behaviors. So it enables change by helping the participants focus on what's important and even more crucial, delivering very rapid results so that the positive feedback loop can be built. The color codes on those sheets that you see in the bottom right They give participants a head up of the developing risks. Some of the issues that Mark has shown, you can see up front 2 days, 3 days, sometimes a week ahead, that there's certain risks developing in certain areas of the mine, which we have to be careful of and that we have to proactively address. So the activities become future focused, and we try and discourage very strongly sessions every morning where we just focus on why were the efficiencies low in this department yesterday, why did this happen, etc. That's water under the bridge. The primary focus of discussions need to be, what do we need to do in the next few days to make sure that the production flow, and especially through the bottleneck area, is not affected detrimentally at all. So even more important, this creates an environment where participants can hold each other accountable for the performance and for supporting the performance of the bottlenecks. And this is the classical peer-to-peer accountability. It is crucial. We find that peer-to-peer accountability works far better than trying to get top-down accountability through the system. And this is typically what the results look like once a productivity platform is set up. And you can see it's going onto that green curve where you lift the production, you get that hidden capacity out of the system because you know where your bottlenecks are. And also the system runs more stable. Now, of course, it is possible that when you tend to fall back to the old way of managing and doing things, that you'll go back on that blue curve. But that's the whole purpose of that flow room, is that the thinking and the behaviors get practiced all the time so that that doesn't happen. And the other great benefits that you get from this, of course, is that you free up management time, because if you can start looking forward towards problems that are coming down the track, management time is freed up. Managers are able to delegate with low risk to their subordinates because they will see if things come up that need their attention. They don't need to micromanage their employees anymore. And of course, employees, when they are able to see what their impact is on the results of the mine itself, that is great for engagement. So now that the mine is able to reliably deliver a higher output, the optimistic targets that we talked about before actually become realistic. Because remember, the budgeted numbers weren't pulled out of thin air. There was a reasonable chance from the people that looked at setting the system up that those budgeted numbers can be realized. But as Mark has shown, due to the particular dynamics in the mine and the particular way that we tend to manage our mines now, it can be problematic and we don't reach that. And finally, going back to the original slide, we align the incentives of the production and the planning by making sure that the operational KPIs are more focused on global outcomes, not on the local ones. So we don't have to worry about starvation and blockages anymore, because the people dynamics and the coordination is dramatically improved. In other words, we have connected our silos. So I'd like to say thank you very much. That's what Mark and I wanted to talk about. I'm sure that you have got lots of questions. So if you have a question, I think perhaps see if you can put it into the comments, and we'll take it from there. And look, if it's easier to just ask a question, you're welcome to do that too. Just out of interest, did it come across clearly that what Mark and I are saying are two sides of the same coin? So Mark is explaining the mechanisms by which the capacity is lost, and the system that I'm proposing is a system that compensates to a large degree for that. So yes, to some degree you will have buffers, but you will have just enough buffers to protect, especially your bottlenecks, and you won't be wasting buffers by having it in areas, or too much of it in areas where you don't need it. But definitely, given the interdependency and the variability that we talked about, you have to have some level of buffering, and you do need excess capacity to catch up, because Murphy is going to hit. That's a guarantee in mining. And mining is different from things like manufacturing, where you have a significant amount of control over your environment. In mining, the geology, no matter how good your drilling patterns, etc., you are going to get a surprise, and your system needs to be able, and your people, they need forewarning, and they need to be able to react proactively, because once they're on the back foot, as Mark explained, it's a spiral that gets worse and worse.
Okay, we've got some questions happening, Hendrik.
Right.
I reckon I'll let you have a read while I answer one of them. I think the first question probably fits in your space. I'm going to answer Paul's question about what can be done to reduce the inherent variability of the processes. I tend to think that so much of what we're talking about and so much of the change that needs to happen is actually about a mindset change. We have the tools, we measure the data, we have the hardware capability, etc. I actually think a lot of this starts in the mindset, in the way we think. And variability is a classic example of that, in that we don't tend to acknowledge variability much, we don't tend to think about it much, we don't tend to measure it much, and so on. And I've always been a great fan of you can't improve what you don't measure. So I think we actually got to start with acknowledging variability, measuring it. If I think about the series of sequences, series of activities in an open cut mine, where we drill, we blast, we dig the waste, we dig the ore, we process it, and then we rail it and ship it, and so on. I don't think we even understand the different variability between all of those different activities. And undoubtedly, there will be a significant difference in variability between, for example, a dragline operation and railing or shipping, and so on. So you know, I think we've got to start with measuring, and then for me, the next step is understanding the impact of the variability. If we don't understand the impact of the variability, then we don't necessarily tend to understand what you know, how much effort we should make in reducing variability. I think that's the starting point, because then from there we can then look at what's causing the variability and so on. There's lots of things that add to the variability. The silo, certainly the KPIs and the silo effect that we have in the mining industry, where everyone's got their own KPIs, but which are about their throughput rather than the system throughput, and so on. The whole mentality of getting back on plan, there's this massive philosophy in the mining industry. As soon as we get behind plan, somehow or other we have to get back on plan, because the plan was what we committed to, it was what we said we were going to do, so we've got to do it. So as soon as we've got to get back on plan, we take shortcuts and we do all sorts of other things which are just all about getting back on plan. All that does is just increase the variability instead of just running to a drum beat, sort of, and so on. So that's my thoughts on that.
Yeah, thank you. Thank you, Mark. So just on that point, on the inherent variability, yeah, I think that's something that all the big, the tier 1 consultants have been trying. I don't know how successful they've been. So the principles of what I explained and the way of management is set up from the point of view that the variability will always be there, and while we will be able to reduce it, it's never going to go away. We will always have some degree. So what you would typically do is you would set up the system, as I explained, around the bottleneck, and then in the bottleneck department, you would then go in with a lean Six Sigma kind of a project and try and see what you can do to the quality of product that comes much earlier when it comes to that part. But I think it is $1 million question. I think if we knew exactly how to reduce that variability, we would be very wealthy.
I think in the statistical process control world, they talk about special cause variation and inherent variation. So I think inherent variation is very hard to reduce, but there is, in my observation, a huge amount of special cause, just disorganization variation, which
I understand. I understand.
comes from those departmental kind of issues that you...
Correct. And when we have everyone in that flow round meeting for 30 to 40, in the beginning, it's like 40 or 50 minutes a day. It should only be 30, but it's 50 because minds are not set up to have discussions across functions. They are very well run as functional departments, and over the years and months, at the interfaces, the problems start occurring. And also because of the way that we measure people, I mean, if somebody is really under pressure with their KPIs and they're not doing well, the temptation is great to do something that make their numbers look good, but will have a knock-on effect in the next department. It'll probably hit you again when the circle comes around and you're at that position again, but it's survival. So what happens in that flow room when it all becomes visible and you can't hide your behavior, it's very clear, have you helped the flow through the system or have you not? And the way that we lead the discussions are more around dialogue than debate, because debate is, I was right, you are wrong, why did you do this? I know what you should do. I'll tell you how you should do your job better. It becomes an issue of, we all have a bit of understanding of what's going on here. Let's have this discussion around it and understand how this particular issue came through to the bottleneck department, and the variability was greater than it could be. And you tend to also find that the support departments become much more effective once that starts to happen, because it's that peer-to-peer accountability. It takes up the slack that the KPIs can't take.
So Hendrik, first question there from William about changing from balance to introducing capacity.
Yes, it's a great question. Yeah, it's a great question. So I take it it's the issue around the cost implication, because there's going to be a month or a quarter where you suddenly have to put in buffers and bring up more capacity that you've got available, maybe a few parked trucks. And it's going to show on the numbers. I assume that that's the question. So what we tend to do is, there are some circumstances where it works easier than others. So if you have a mine that's been struggling, and where the mine manager is under pressure to deliver, you often find, so we will take them through a 3-hour session of what we condense now into 30 minutes. And we will explain how, in detail, how the problems that they're facing are a consequence. Because when the issues that the balanced capacity chain throws up causes extreme instability and pressure on everyone involved. And our job is to give that mine manager and his employees the confidence to go and try this. And what we would also do is we will go at head office, especially from the finance side. It's first prize to get a chance to take the finance people through this exact example, to show them what is busy happening and what happens when you try and when you try to over constrain the system in order to try and get efficiency. Because what you're doing is you're taking a highly variable interdependent system, and with all the KPIs and efficiencies, you're over constraining the system. That's why the picture was there of the guy in the straitjacket, because you're making it impossible for people on the mine to perform. And what you then ask for is a month, because within a month and a half, the results will come through. And you know, also often, if you're in trouble on the mine, I suppose you don't have an infinite amount of time to turn it around. So very often it's, what have you got to lose by adjusting some of your measurements on the accounting side in another direction, and or in a negative direction as far as the short-term accounting is concerned. Because remember, it's just, if I put in a buffer in the right place, in the right position, it's just a shifting. It's a shifting of the finances that's happening. I've not wasted it. I would have spent that money a little bit later. And it's that discussion that you have to have and show. And strangely enough, your financial managers, once you take them through this, not all of them, but some of them are extremely astute, and they pick it up immediately, because they've also seen cause and effect in their careers, just that they didn't have a way to understand what was happening.
Okay. Another question here from Jody. When are we able to do probabilistic scheduling? So I guess that's something that Barrow, that I've been sort of pushing fairly hard. I can't believe that in 2022 we are still deterministic scheduling from just a default perspective. And so I have had numerous discussions with mining companies and software suppliers and so on. And certainly probabilistic scheduling capability is there. We've had it for a long time. I guess really what I'm talking about is where it's just built into mainstream scheduling software, and it's just a standard part of the process that you can choose to run or not to run just by sort of ticking a box and so on. Now, I guess I don't confess to definitively know, but from lots of discussions, from what I've found so far, it seems that Primavera 6, which is a project management software, actually has the capability. And so I know of one mining company who is taking Primavera 6 and modifying it to sort of suit mine scheduling as distinct to sort of project scheduling and so on. So that's the only sort of one that I know of. But it's definitely something that I know a lot of the mining scheduling software suppliers are currently working on. I spoke to one a couple of weeks back who said that there had never been any demand for it from customers. However, in the last couple of months, the people are starting to ask about it, and so it's on their radar and so on. So hopefully it's not that far away. But I do think that there's a mindset change required to go with it. And I think that we can start the journey in terms of thinking and talking and ranges and variabilities and risks, etc., instead of just talking in sort of fixed single snapshots in time that we currently do. I think we actually can get on that journey while we're waiting for the software suppliers to come through with the goods.
All right, and then the next question is there's one from Craig. Craig, this is a great question. What are the thoughts on evaluating debottlenecking projects, and so moving the bottleneck to a different part of the process, or where the bottleneck should be in a new mine scenario? Now, there's two ways to look at that. First of all, the bottleneck should ideally be your most expensive part of the process, or the part where it is most expensive to put in new capacity. And that's almost always on the plant. The plant costs billions to erect. And although your trucks and your dozers and your drilling and on the mine operations side is also expensive, it's not nearly as expensive. And yet you very often will find that trucks are parked to get the efficiency better, and then the mine part is actually where the bottleneck is, and the plant from time to time is staffed. The most expensive part should never be staffed. So ideally it should be at the plant. When we do an implementation, and let's say it's that graph that I showed you where the outputs are very unstable and you got moving bottlenecks. As we start in that process, very quickly within a month from the color patterns, the eye can pick up very easily where the bottleneck is, because often, honestly, nobody knows. You can go and look at the official numbers, but that won't tell you that either, because of, as Paul said, there are people and policy issues very often involved. So as soon as you see where that bottleneck actually is, you already will start to do work on trying to lift the capacity of that, but also more importantly, to understand where the bottleneck is going to shift to, because you never want to be caught by surprise with a bottleneck shifting to a new position. You want to know where it's going to shift to, and you want to have everybody ready and trained for when that happens, because otherwise it will have a significantly negative effect on your production. So I hope that answers the question.
All right, question from Sam. Do you have a feel for the allocation of variability on account of, for example, resource, environment, systems, and other categorization? And that's a really good question. I don't have anything. I have started calculating variabilities. I've started collecting data to compare planned variability against actual variabilities and so on. I haven't broken that variability down further and subdivided it yet, but that's something that I'm sort of keen to get into as we move more into the variability world of measuring and understanding impacts and so on. Not sure whether you've ever done anything in that space, Hendrik.
No, it's as you say, this is a very tricky thing, and it's something that the people that work on the actual mine, because the one thing that's interesting about mines is that they are similar and yet they are different. So, and that's why, in my opinion, why many of the tier one consulting interventions don't always deliver the value it should, because it assumes that one mine is very much like the next. And what the theory of constraints and what you've seen today shows you is that everything depends on the geology of this particular mine, the design, and what kind of equipment is there, how old they are, what's the history of everybody, what's the history of the mine, how did they get to where they are now. So it's extremely dependent on the actual mine, and any method that doesn't take into account and work with those working on the mine itself with the experience hands-on, it's going to be problematic just because of this variability. And it's something that I'm always surprised is that people try and copy things from the manufacturing area. And I'm not saying you can't copy anything, but it is a very different environment in a manufacturing plant, given the level of control that you can exert compared to a mine.
All right, 2 questions from Riza. Does probabilistic scheduling also apply to long-term mine plan, or is it only for short-term plan? I actually think that probabilistic scheduling applies everywhere, but it's much more critical in the short-term space than it is in the long-term space. I tend to think of plans, I tend to categorize plans as execution plans. They're really short-term, sort of from 2 weeks down, that you're actually going to try and implement. Decision-making plans, which sort of are from a month out to sort of a couple of years or something. And then I think of life of mine plans much more for information, as well as longer-term decision-making and so on. But it's that short-term plan where it's critical to make the right decisions, because they directly impact on costs effectively straight away. So for me, I would like to see it in the short-term space, and then the long-term space can come later to some extent. Second question is, 5 days buffer the best number based on historical experience or just an example? Yeah, that was just a very simple example that I kept as simple as I could to some extent. And I just wanted to try different buffers and so on. Size of the buffer is actually dictated by the variability of the upstream tasks and the downstream tasks. So if we get serious about these things, it actually just comes back to the risk, because the size of the buffer dictates the risk of the downstream activity having to stop. And so it just becomes a risk decision as to how large a buffer do we want to carry in terms of the downstream process stopping and so on. So if we get serious about things, we actually get into risk decisions and so on.
Right, and then Colin asked the challenge for a green scheduler where they're not given support to develop an effective mine plan, and then especially when I suppose things change in the mine environment, that means that certain assumptions can't be used anymore. And he's mentioning the use of digital twins. So that's something that we've also started doing the last 4 or 5 years. Once everyone understands the theoretical principles, it becomes very effective to use the twins. Definitely, you want to model different potential decisions around your bottleneck, and you want to see how different ways of working will impact it. And once you've got that capability, of course, you can help visually show why certain counterintuitive things are actually important, because I think that's often the problem. I sometimes think that the most dangerous person on the mine is somebody that's just done an MBA and is now busy running the mine with financial principles that they've learned. They don't translate directly always, and one has to there's some very surprising things that can come out, counterintuitive things. And yeah, for that, the digital twins, if you've got it, it's very useful.
Yeah, and Colin, you rightly point out the concerns about green or inexperienced schedulers and the issues there, and the sort of the likely shortage of skilled labour in the mining industry. And I must admit, I do find that a major concern going forwards. I think that the planning engineer, certainly the short-term planning engineer, is one of the most underrated roles on site. I actually think it's a critical role on site. Yet we have these sort of processes where we just roll engineers through there and we put junior engineers into the role and so on. We should never put junior engineers into a short-term planning role. That just shows to some extent our lack of importance assigned to the role. I mean, I know often we're dictated by turnover of staff and all sorts of things, but I do think that we undervalue the role, and so I do find it a bit scary. And then particularly, yes, if we want to upgrade the tools that we're using and so on, we've got to upgrade the people with them. Now, there's a question from Jason Hendrik, you mentioned industrial processes tend not to follow normal distributions. What modes of output would you say are common in mining operations?
Well, I'll have to guess. It's not something that I've studied in detail, but the graph where I showed you that sometimes you get 12 and often you get 0, I think where you have a breakdown, I must say I can't answer that question in detail. And fortunately for the way that we look at the system, it's not absolutely crucial. It would be for the way that Mark is doing the calculations. But for what we're doing, it's not a train spat if we don't know exactly. We just need to understand it's not a tight normal distribution. It's something with a very long tail. We just think so. And just to come again, so this whole discussion that we've had today about optimistic mine plans and production not always following them, etc., etc. These issues, and it includes things like engagement and pressure at work and safety risks, etc. They are all consequences of trying to run mines in a way that seems very logical and seems to work in manufacturing, but it does not work in mining. And the crucial part is not necessarily the techniques. The crucial part is conceptually getting that understanding across to decision makers, so that when people on the ground start to work in a different way, in a way that's much more relevant for the environment in which they are, that they will be allowed to go for a month or two. And by the time the results are there, nobody cares how they did it. Everybody is happy with the results. But there is that 1 to 2 months window where, and sometimes it helps to get an outside entity in to fully explain and articulate what people on the inside can't do. And I suppose also if you're on the inside and you're under pressure, people tend not to always want to hear what you've got to say, because it might sound like you are like you're looking for excuses. I mean, mining, it's very often it's high value is put on people that can just make a plan and get it done.
That's it for the questions that I can see, Hendrik. I don't know whether you've got any others there.